Once again, good morning, everyone. So we have seen two methods to build the nodal admittance matrix of a given network, right? So we came to understand that given a complete network and how to form the Y-bus for that complete networks is known. Okay, either by direct inspection method if we don't have mutual couplings, and singular transformation method if we have mutual couplings between the transmission lines. Okay, now knowing this, let us actually in practice we normally come across a slight modification of the Y bus, not repeatedly building the Y bus to perform the load flow studies, but we need to form the new Y bus from the existing Y bus. So suppose we have a network like this, and the Y bus is already formed. Y bus is already formed. Now assume that, not assume, it is real that this network is very big in size, and with large number of nodes or buses. Okay, thousands of nodes or buses, right? So I have a network with me and I have already built its Y bus. Okay, now as a system engineer, he is carrying some contingency analysis, some analysis on this power system. Okay, some analysis on this power system which requires repeated load flow studies, right? Repeated load flow studies, and in these load flow studies the network configuration is different. Network configuration means how the lines are connected among the buses and what is its connectivity diagram. Okay, now the system analysis is assuming that there is a fault on one bus and this is removed, this line is removed, and which means that the network configuration is altered. And he needs to form the Y bus to conduct the load flow study, and he wants to, from the load flow study again, he wants to see what will be the bus voltages, what will be the new line flows, and what will be the power losses in the network. So these analyses he will be carrying by assuming that there may be some fault in this line and he has removed this line, and now he is visualizing the network behavior. Now similarly, next time what he do is he restores this line and he treats the fault is now happening in some other line, and this is opened, and again new network configuration has appeared. Again he wants to find the Y bus and find out the load flow studies. So that means he repeatedly wants to calculate the load flows under different types of contingency or faults at different locations, right? Now for this you need to have the Y bus for the deformed network or modified network configuration, right? Now in that sense you don't use direct inspection method or singular transformation method to form the Y bus. No, he is not going to use. What he is doing is, this is tricky, right? So he tries to already use the existing Y bus of the complete network and tries to add or subtract the okay, so add or subtract a submatrix, a small submatrix corresponding to the eliminated line, or I can add one more line, not only eliminate, not only subtract the this submatrix of corresponding to this line to the existing network, I may also add one more line. In that case, I will be adding this small submatrix corresponding to this line to this existing Y bus. Okay, so that is how with a small number of calculations I can form the new Y bus. Okay, right? This is the concept, and this is most widely used by the system engineers. Right now, how do they do? Let us proceed. Now let me yeah. Now in the network we have three types of connections. One is line connected to bus and reference bus. Any bus to reference bus, line connected between two buses. Difference is now not there in this. Okay, and third one is line connected between or mutual coupling, mutual couplings exist. Okay, now these three cases, if you can find out its submatrix, I say instead of saying submatrices, I say the building blocks. Okay, right? Now let us find out one by one to this. Once I have this, then I can add or subtract any line to the existing system and try to alter the Y bus accordingly. Right? Now first let us take a bus. A line is connected between a bus I to reference. Right? Let it be having a primitive admittance of YA, and a branch current is YA, and a branch current is flowing through it is IA, and a branch voltage drop is taking place is VA. Right? And this is bus I, and let us assume that the current injected into this node is II. Okay, and the bus voltage is VI with reference to some reference node. Okay, so I have defined primitive variables and I have defined the node variables. Right? Now if I write down primitive admittance form, for this connection, then it will be simply what is that, IA is equals to YA into VA. Right? And if you do the same analysis what we have done, that is getting the relationship between the nodal voltages and the primitive branch voltages, and also the relationship between the nodal currents and primitive currents, and then again transform this to the nodal admittance form. Okay, you will have simply I is equals to Y into VI, where this Y is also equals to YA. Simply now, because this is a single element, and this matrix having single element, and its node is ith node. ith node like this. Okay, so this is a single element vector like this, right? And this y element yii is simply equals to ya, right? So a branch or line connected between in a bus to reference, its nodal admittance form is simply ii is equals to yii vi of all single elements. Okay, right? Now this is the building block, this is the building block. Yii is equals to ya is the building block for this type of connection. Okay, now let us move to the second connection. The second one is, assume that a line is connected between nodes m and n. Let us assume that a line is connected between nodes m and n. Now this is reference. Now first I am representing the nodal voltages and currents. Nodal voltage Vm, nodal voltage Vn, nodal injecting current Im, and nodal injecting current In. This is the reference, right? And the branch, let us assume again same Ya, Ia, and this is Va. Okay, now this is branch connected between two nodes, right? Now under this condition, what is the primitive form? I use the same logic again. Primitive form is, what is that? Ia is equals to Ya into Va. This is the primitive form. Let us assume that this is equation 1. Now I want the relationship between voltages Va versus Vm and Vn. So what is that relationship? So we have Va is equals to Vm minus Vn, right? So putting in matrix form, Va is equals to Vm Vn. So I have 1 minus 1, 1 minus 1. Okay. Now similarly I want to have the relationship between In versus Ia. So what is that it is giving? Im is equals to Ia and In is equals to minus Ia. So from this, if I write down In, this is Ia, so I have this is 1 and this is minus 1, right? So if this is A, this will be A transpose, right? Now coming to the, so this is the second equation and this is the third equation. Now combine these three. So if I place this Va by this equation, so I have Ia is equals to Ya into this A matrix multiplied by Vm Vn. I have just replaced this Va. Now we know that Ia multiplied by this A transpose. So I multiply A transpose on both sides. A transpose, not plus. Now I know A transpose A is equals to this matrix, that is Im In. So it means that Im In is the nodal vector, current vector, is equals to this A transpose Ya and A now forms the Y bus, Y bus, and this is VM VN. Okay, right? Now what is Y bus here? If you try to form the product of this A transpose YA into A, you will be getting 1 minus 1 minus 1 1 into YA. Now this is the expansion of Y bus, that is 1 minus 1 minus 1 1 into YA, or YA minus YA minus YA in YA. So this is the Y bus, right? Now the building block for a branch connected between the two nodes or buses is simply, that is 1 minus 1 minus 1 1 into YA. What is YA? The primitive admittance of that line, right? Now this is equals to Y bus. And in earlier case, what is Y bus? Now find, mind you, you have to note the numbers, node numbers. This is M, this is N, this is M, this is N, right? Node numbers are always important to form the Y bus. Okay, now in previous case it is simply Y bus is equals to only single element, that is YA. So Y bus is simply YA. Okay, now we have now completed two cases. One is line connected between the bus to reference, one is line connected between two buses. Now let us assume the third case, the mutual couplings between the lines. Okay, so again this is the line connected between M and nth node with YA as primitive admittance, current. Let me put in now, instead of admittances, let me put in ZA, impedances. This is IA, and this voltage is VA. And we also have one more line whose which is connected between P and Q nodes, right? And whose impedance is, primitive impedance is ZB, and this current is IB, and this primitive voltage is VB. Okay, and let me indicate the nodal voltages and currents. So this is VM, this is VN, this is VP, this is VQ with reference to some reference node. Okay, mind you, always nodal voltages are referred with reference to some reference node. Okay, somewhere there is some node, reference node is there. Now injected currents, this is IM, this is IN, and this is IQ, and this is IP, right? Now same logic, you write the primitive form of equations and then try to convert into nodal form. Okay, so primitive form I say, okay, VA is equals to ZA IA plus you have the mutual coupling, mutually linked, that is ZM. Okay, now ZM into IB, and VB is equals to IB, ZB into IB plus ZM into IA. Okay, so putting this in matrix form, you have VA VB is equals to IA IB, this is ZA ZM ZB. Okay, now see, if I want to convert this primitive impedance form to primitive admittance form. Okay, admittance form is YA YB is equals to, okay, now let me not write here 1 by ZA or something like that. Let me this is Y bus. Let me put this is VA VB. Now this Y bus is actually inverse of this Z, ZA, ZM, ZB. Okay, inverse, mind you. It is not, this first element is not 1 by ZA and second element is not 1 by ZM. Okay, but the entire matrix should be calculated by taking the inverse of the impedance nodal primitive impedance matrix. Okay, sorry, this Y, not Y bus, this is primitive, sorry, this is Y primitive. This Y primitive is inverse of this Z primitive. Okay, not just a reciprocal of the elements. Note, right? So once I have this primitive form, that is IP is equals to YP into VP. Okay, this is my first equation. Okay, now again same, use the same voltage relations and current relations. Voltage relation, let me do this one because it is mutually coupled. Let me do this one. So I want voltages VA. What is VA? VA is VM minus VN, and VB is VP minus VQ. Okay, now if I transform them into a matrix form, VA VB, so nodal voltages are VM, VN, VP, VQ. So VA is VM minus VN, not related to VP, VQ, and VB is VP minus VQ, not related to M and N node voltages. Right? Now this is A matrix. Now this is VP and this is V matrix. Okay, so this is VP related to A times V. This is second relation. Now coming to the current relationships. So what is that? Let me write down nodal currents. IM is equals to IA and IN is equals to minus IA, and IP is equals to IB, and IQ is equals to minus IB. So putting these relations in matrix form, so I have IM N P Q in terms of IA and IB. So IM is IA, right? Let me, I have to put this like this. So IM is simply IA, and IN is simply minus this is 0, this is minus 1 0, and IP is IB, and IQ is minus IB. This is like this. So this is, this vector, this matrix is A transpose. If you notice that, right, 1 minus 1 0 0, 1 minus 1 0 0, and 0 0 1 minus 1 0 0 1 minus 1. So it is A transpose. So we have third relationship. So if you see, write on, coming back to the primitive representation, put this VP is equals to A times V, that is IP is equals to Y primitive, VP is A times V, right? But what is this? This is IAIB, they are I primitive. This is A transpose. Now this equation I am writing, this equation is I vector is equals to A transpose I primitive, right? Okay, so this is I nodal vector is equals to A transpose I primitive. So if I multiply A transpose on both sides like this, A transpose, now this will be equals to the nodal vector I, which is equals to A transpose Y primitive A times V. So if you take the product, Y primitive is the inverse of Z, Zm, Zb, and A transpose this vector, A and A transpose vector, then you will have, that is Im, In, Ip, Iq. Let me write down. Let me write down here. Okay, I'll write on the next page. Okay, if you take down, this is I is equals to A transpose Y primitive A times V. Okay, so where Yp is Z inverse of Za, Zm, Zb inverse, and A is equals to ఏంటమ్మది A ఏమొచ్చింది మనకి, what is that A? This is A, 1 minus 1 0 0, 1 minus 1, so 1 minus 1 0 0 0 0 1 minus 1, this is A. Now if you substitute here and you expand this one, you will be getting, let us assume that now this is Yp is equals to now Ya, Ym, Yb, right? Not this Ya is not equals to 1 by Za. Okay, mind you, after taking the inverse of this matrix, if I represent the first element and diagonal elements like this, then this is Ya, Ym, and Yb. Okay, now so if you substitute this matrix and this matrix here and expand this one, you will have like this. So this is Im, In, Ip, Iq, nodal currents, nodal voltages, Vm, Vn, Vp, Vq. So nodal currents and nodal voltages, and this expansion is simply, I can write down here Ya minus Ym minus Ym Ya, and this is Ym, sorry. This is minus Ya minus Ya, Ym minus Ym minus Ym, and Ym minus Ym minus Ym, Yb minus Yb minus Yb, Yb, or otherwise you can remember like this, right? This is 1 minus 1 minus 1 1 into Ya, 1 minus 1 minus 1 1 into Ym, 1 minus 1 minus 1 1 into Ym, and 1 minus 1 minus 1 1 into Yb. Okay, and the node numbers, these are the M, N, P, Q nodes, M, N, P, Q nodes, right? Similarly here M, N, P, Q, M, N, P, Q nodes. So this is I vector and this is V vector. So now this is the Y bus corresponding to the two lines connect having mutual couplings. Okay, so they are the two lines having mutual couplings like this with Ya and Yb and Ym as the mutual admittances. Okay, now this is the building block. This is the building block for these two branches connected between M N nodes and P Q nodes, right? Okay, now once you have these building blocks for the different branches, whether it is connected between the node to reference or a branch connected between the two nodes or two branches having mutual couplings and connected between something like M and PQ like this, then you can what do you say can build the entire Y-bus also, but normally it is used for building the entire Y-bus, but only to modify the existing Y-bus when there is a addition or removal of a branch. Now what we do is, first we try to build the Y-bus. So this is the same network I am working on, right? And we have also given the values for these admittances, line admittances, right? Let us not take the admittances right now. Okay, now what we do is we try to write down the building blocks for these branches one by one, and we can join them. Okay, now let us write down one by one building block. So first A branch A. So what is its building block? It is just connected between the node and the reference. So its building block will be single element, which will be I is equals to YA into V. So what is this? This element is this is bus 3, right? So this is the building block for branch A. Okay, so this is okay, let us I3, this is V3, putting in more appropriate. And what about building block for branch B? Branch B and branch C are mutually coupled like this. So branch B and branch C are mutually coupled, and now they are actually connected between bus 3, 2 and 1, right? Now one bus is common here. In this case one bus is common. Okay, no, don't worry, this is YB, this is YC, and this is, let us assume that this is YM, right? And what is the building block for this one? This is 3, B is 3 2 and C is 3 1. This is 3 2 3 1, right? So this will be 1 minus 1 minus 1 1 times this is YB, and 1 minus 1 minus 1 1 times YM, and this is 1 minus 1 minus 1 1 times YM, and this is 1 minus 1 minus 1 1 times YC, right? So this is I3 I2 I3 I2, this is V3 V2 V3 V1, this is I1 I3 I1. So this is the building block for the branches actually having mutual couplings. So 3 branches are over, this branch over, these 2 branches over. Now let us write down the building block for the DA element, that is, it is connected between 2 and 1 or 1 and 2. So it will be simply I1 I2 1 2 1 2 v1 v2, this is simply I write down 1 minus 1 minus 1 1 multiplied by yd multiplied by yd, right? Multiplied by the branch admittance, right? So this is the building block for this element. Now similarly, if you write down the building block for E and F, okay, E and F. So building block for E is 2 and 4. I2 I4 is equals to 2 4 2 4 1 minus 1 minus 1 1 into YE V2 V4. And similarly for F branch, that is 1 and 4, I1 I4 1 4 1 4 1 minus 1 minus 1 1 into YF multiplied by V1 and V4. This is building block for F branch. Now the G branch is again similar to the A branch, which is connected between 4 and the reference. So simply I4 is equals to, this is YG, this is 4 4 multiplied by V4 multiplied by V4. Okay, now I have the building blocks for all the branches, right? All the branches. Now simply you can write down the Y bus of this 4 by 4 matrix, because we have 4 buses, 1 2 3 4. Okay, now you put these elements corresponding in this. Suppose if I want to put this YA at 3 by 3 3 3. So 3 3 means this is YA, right? Now next, actually you have to reduce this one. You have to reduce this matrix to I1 I2 I3 and V1 V2 V3. You have to reduce. Okay, now this will come here, and these elements 1 2 3 1 2 3 elements will be forming here. Again, you 3 by 3 means you have to add the element corresponding this element, you have to add here. And similarly these elements, this is between 1 and 2, right? So 1 this building block 1 2 1 2. So you have to add 1 1 1 2 1 2 plus 2 2, right? This building block is added to the corresponding elements, previous matrix plus these elements. So similarly this is 2 4 2 4. So again plus 2 plus 4 plus 2 4 plus 2 4. So these elements will be added corresponding to this branch, this building block. Similarly 1 4 1 4. So plus 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 plus, and finally 4 4. Okay, so you do this problem. I have given the procedure, right? How to write down the building blocks for each branch, and just add corresponding elements to the Y bus. Okay, so again take this as a small exercise or assignment too. You take the same admittances, line admittances I have given in the previous problem, and try to write down the building blocks like this, and add corresponding to the Y bus elements. And if you do and you simplify this one, you will get simple 4 by 4 matrix, which should be equals to the previous Y bus you have found in the first assignment. Okay, now what I have said here, I have started the building blocks based on only to alter the existing Y bus, right? And I have ended up here with forming the Y bus using the building blocks. Okay, you can also do this method. You can also apply these building blocks to form the complete Y bus, but this is not actually done. Only for our verification and cross verification, you try to form the Y bus for writing the building blocks for all the branches using the previous problem values. Okay, and verify this Y bus is equals to the first assignment Y bus. Now I'll stop there. But if suppose I have given the network like this, I have given the network like this, and I have already formed my Y bus, and I say that there is a fault taking place in this D branch connected between 1 and 2, and my circuit breakers are opening this fault branch like this. Now what will be the new Y bus for the new system? If I ask you like that, what you do? Simply you write down the building block for D branch. What is that? Where is that? D is between 1 and 2, so this is 1 and 2. You write down the building block for this D branch, and you have to subtract this small submatrix building block from the existing Y bus. You have to subtract this building block of 1 minus 1 minus 1 1 into YD from the existing Y bus of the system to get the new Y bus. Okay, so similarly, if I remove any branch, you write down the building block for that, and just subtract that block from the existing Y bus to get the new Y bus. That is the conclusion of the third method. Okay, what is the third method? I have introduced building block method, but this is only to modify the building block method, only to alter the Y bus, not for completely building the Y bus. Now I will take 2 minutes quickly and finish up this Y bus formation. Now you have I is equals to Y bus into V as a nodal admittance form of representation of this network. Okay, now given current injections at all the buses, given current injections, net injections, I said net injections, there may be loads and there may be generators. I am talking about net injections into the nodes. So given any values, this vector is known, this matrix is already found, then I can find out the bus voltages either by simply taking the inverse of this Y matrix multiplied by this known vector I. This is the first method to find out the network solution. I am talking about network solution. What is that? By taking the inverse of Y bus. But this method is not at all preferred. This method is not at all preferred. Okay, because Y matrix is so sparse in nature, and it is having a complex terms, entries. So that is why taking the inverse is very difficult, because some elements in the diagonal elements may become sometimes 0, right? So it is very difficult. Okay, now the second method is successive elimination method. successive elimination method, what you do is you have to form the uh, the lower diagonal off diagonal elements to 0, right? You have to make all the entries here 0 1 by then by using the successive elimination method. Okay, and once you have the upper diagonal matrix, this matrix, and by successive substitution, right, you can find out the solution for V. So Vn is equals to this element into this current. You know, this current is known and this is the only element, then I can find out V1. Now next n minus 1th row, you have these two entries here, and this element into this current plus this element into this current gives Vn minus 1. Already we have calculated Vn, so it is easy to find out V1. So by successive substitution, you can find out the complete vector up to V1. Now this is the successive elimination method to make the lower triangle to 0, and you can find out the solution of the network bus voltages. But the only problem with this method is, if I want to calculate the solution for repeated number of injections, at one time I have given one type of injection vector, and at some other time I have given some more injection vector, right? So if I change the current vector, and I want to find out the solution, I have to do the successive elimination procedure repeatedly, so which is time consuming, and the requirement to conduct the load flow studies repeatedly with vast number of so many number of times for a given interval is not achieved by this successive elimination method. Okay, because you have to conduct this elimination method for each injection, right? Now the third method, which is most widely used, is LU decomposition method. Okay, now this is most widely used method, and this is not required. Once you find out the Y bus into LU factors, the lower triangular matrix and upper triangular matrix, the product of this LU will be equals to the Y bus. So there is a MATLAB program to decompose Y bus into LU factors. So once you have this LU factors of Y bus, and I say these LU factors, you can find out the LU factors by using one successive elimination procedure. Once you do this procedure to find out this LU factor, then it is done, right? Now once you have these LU factors, then I is equals to actually Y bus into V vector. Now I represent this as LU into V. This is V, right? Now I treat this product, I treat this product as unknown vector, V prime, right? And I is equals to L into V prime, right? Now once you have this solution for V prime, now what is V prime? V prime is equals to U into V. Now I want V, so take the inverse of U and multiply with So this is V is equals to U inverse V prime. Okay, so V prime is already calculated. So multiply this two matrices vector product, and you get the ultimate final vector of the bus voltages. Okay, so this is only once required. LU factors you have to calculate only once by one successive elimination method. Once you have these two factors, now for any given injection vector, you can find out the bus voltages just by two substitutions. I say two forward substitution and reverse substitution to find out this complete bus voltage vector V. Okay, this is the idea about the network solution. Brief idea about network solution by matrix inverse, successive elimination and LU decomposition.